Hello all, today I will work on exercise set for section 14.7. I will choose problems from our textbook. I plan to do number 6, number 7, 6 and 8, and then number 12, number 16, 30 and 32, 40. I think 40 we have some ways to do that. Number 42 and then 47. I think that's the last one. Yeah. Let's see. Let's try to work on this. Number 6. You know what? Let me do it here. Below that, number 6. We have fx for fxy equals to xy minus 2x minus 2y minus x squared minus y squared. Okay, first we need to find the critical points, right? And that is by finding the first partial derivatives respect to x and respect to y, set them equals to 0. Set this equals to 0. So we get y equals to 2x plus 2 and x equals to 2y plus 2. How do we solve this? Let's do substitution. Call this equation 1, equation 2. So equation 1 into equation 2 gives us x equals to 2 times y, which is 2x plus 2 plus 2. X equals to 4x plus 4 plus 2, that's 6. So negative 3x equals to 6, x equals to negative 2. And when I plug that into equation 1, y equals to 2 times negative 2 plus 2, y is negative 4 plus 2, that's negative 2. So the critical points, or critical points is negative 2, negative 2. Okay, we have only one critical point, huh? Before I go on, I would like to explain a little bit for intuition. Notice that for this function here, it is symmetric with respect to, this is symmetric with respect to y equals to x plane. What do you mean, Thomas? Here's what happens. Suppose you swap the position for x and y. So x becomes y, y becomes x. Notice that we actually get the same thing. That's equals to fxy. Okay? Now, basically, whatever happened to x will happen to y also. At least when it comes to critical points, you will have some of the coordinates must be that symmetric one. You see the x equals to y then, right? Okay. Now, of course, this is something you still need to show, but it will be nice if before we start working on that, we already have some feeling, you know what, because it's symmetric with respect to y equals to x line, or in 3-dimension y equals to x plane, then the solution will be having x and y coordinate equals to each other. Okay, that's the critical points. Let's go on with the second part. Because they don't tell us the boundary, then we need to use second derivative test. Second derivative test. Yeah, because we need to find the local maximum, local minimum, and saddle points, right? So f sub xy of xy will be 1, yeah, it's 1. F sub xx is -2. F sub yy should also be -2, huh? So the Hessian will be -2 times -2 minus 1 squared. Therefore, the Hessian at -2 comma -2 will be still 4 minus 1, that's 3. That's positive, means we have either local maximum, local minimum, right? And since f sub xx of -2 is -2, so we have local maximum, right? Local max at -2, -2. And the local maximum is f -2, -2, which is, what's that? That's -2 times -2 minus 2 times -2 minus 2 times -2 minus -2 squared minus -2 squared. Oh, that's a lot of -2's put together. This is 4 plus 4 plus 4 minus 4 minus 4, that's equals to 4. Okay, so that's the local maximum. Actually, at the same time, notice that the Hessian basically tells us that the graph is concave down all the way, right? Let's try to sketch this. Let's try to sketch this. So I will use my graphing software to graph that. C equals to xy minus 2x minus 2y minus x squared minus y squared. Yeah, that's what it looks like. Okay, that's what it looks like. Let me screenshot that. Then bring it to our paper or notes. Let me put it here. Where the vertex there is positive 4 at -2 comma -2. Okay, that's what it looks like. Okay, that's for number 6. Number 8, fxy equals to x times e to the, let me write it down here, number 8. fxy equals to x times e to the -x squared minus y squared. Do I copy the question right? Oh, 2x squared, -2x squared minus 2y squared. So first part is the critical points. We do the partial respect to x. Yeah, notice that this is, I will do product rule. This is the first factor, this is the second factor. So the product rule will be 1 times e to the -2x squared minus 2y squared plus x times the derivative of e to the blah times the derivative of blah e to the blah times the derivative of that blah is -4x. So this is equal to, let me factor the e to the blah. Okay, and then that's 1 minus 4x squared. Now I will set this equals to 0 later on, but let's leave it like that for now. How about f sub y of xy? That's x e to the negative 2x squared minus 2y times negative 4y. So if I make it look nicer, this is negative 4xy e to the negative 2x squared minus 2y squared. Now I will set this equal to 0. So I get this equation here. E to the negative 2x squared minus 2y squared times 1 minus 4x squared equals to 0. But exponential function is always non-negative. I'm sorry, it's always positive. Right? So the only way this can be 0, this equation be 0, is when 1 minus 4x squared equals to 0. Okay, so we get x squared equals to 1/4. So x equals to plus minus 1/2. Okay, now that's from the first equation. From the second equation, we see when we set this equal to 0, notice that, you know what, let me do it in the other line. When we set this equal to 0, negative 4xy e to the negative 2x squared minus 2y squared, set it equals to 0. Notice that either x equals to 0 or y equals to 0, but this guy here always positive, right? On the other hand, we know that from equation 1, x cannot be 0. Now from here we see then the critical points must be 1/2, 0, or negative 1/2 and negative 1/2, 0. So we have two critical points here. Then now we apply second derivative test. F sub xx of xy will be, oh, this is so tedious, huh? Okay, so I will start from here. The derivative of this times this will be e to the negative 2x squared minus 2y squared times negative 4x times 1 minus 4x squared plus e to the negative 2x squared minus 2y squared times the derivative of that 1 minus 4x squared, that's negative 8x. If I make it nicer, this will be e to the negative 2x squared minus 2y squared. And then, what would that be? 16x cubed minus 12x. Am I right? Actually, I can factor the 4x out though. 4x times 4x squared minus 3 times e to the negative 2x squared minus 2y squared. F sub yy of xy will be, so it will be this guy times this guy. Is it right? Okay, so that will be negative 4x e to the negative 2x squared minus 2y squared plus negative 4xy times e to the negative 2x squared minus 2y squared times negative 4y. If I simplify, I and then plus, is it right? No, not 16. By the way, the first term is not that one. The first term is only negative 4x. The second term is plus 16xy squared, right? Which means I can factor the negative 4x out. Negative 4x times 1 minus 4y squared. Is it right? E to the negative 2x squared minus 2y squared. Okay. Okay, that's for the second partial derivative respect to x and x, the respect to y and y. Now f sub xy of x comma y. I need to take that f sub x and do the derivative respect to y. So when I do the derivative respect to y from that f sub x, that will be basically that thing multiplied by negative 4y. Okay, so e to the negative 2x negative 2y squared times negative 4y times 1 minus 4x squared. Okay, seems like all the x's have squares anyway, so I can take care of the Hessian for plus minus 1/2 comma 0 will be, let's see, f sub f sub xx, that will be 4 times, oh, you know what, I cannot make it together, I need to separate that. Let's do the plus 1/2 first. 4 times 1/2 times 4 times 1/2 squared minus 3 e to the negative 2 times 1/2 squared minus 2 times 0 squared times f sub x, f sub yy, that will be times negative 4y, I'm sorry, negative 4x times 1 minus 4y squared times e to the negative 2x squared minus 2y squared minus f sub xy, that will be e to the negative 2 1/2 squared minus 2 0 squared negative 4 times 0 1 minus 4 times 1/2 squared, the whole thing here being squared. That will be, this part here will be what? This will be 2 times negative, this is 1 minus 3, that's negative 2 times something positive times this thing here will be negative 2 times 1 times something positive. Remember, I just need the plus minus, right? Okay, minus this guy here is just 0 square. Okay, so this is positive, right? Yeah, that's positive because this is negative times negative is positive minus 0 squared, that's positive. Anyway, but this guy here is negative. So f sub xx of 1/2 comma 0 is negative. Now from there we see that that's local max, huh? That's local max at 1/2 comma 0. Now similarly with the Hessian for negative 1/2 comma 0, that will be 4 times negative 1/2. Okay, but this guy here will be -2, this guy here will be positive, times, so I'm talking about this guy. I'm talking about this guy. This guy here, if I replace the x by -1/2 instead, I will get this. Okay, and then I go on with f sub yy. That will be -4 times -1/2. Okay, and then times 1 times something positive minus 0 squared. Okay, but this guy is positive, this guy is also positive, positive minus 0 squared, that's still positive, but because f sub xx of -1/2 comma 0 is positive, so there will be local minimum at -1/2 comma 0. Okay, and then if you want to find the value where it is local max, local mean, you just plug in f1/2 comma 0 and f1/2 -1/2 comma 0. Okay, I expect to get the same value, opposite same values. So there will be what, x is 1/2 and then e to the -1/2. That's the local max, and then -1/2 e to the -1/2 will be the local minimum. Okay, that's for number 8. Too bad it's not symmetric with respect to x equals to y line, right? So we may have different, you see that the critical points does not have x equals to y situation. However, when you look at the next one, number 12, oh, you know what? How about we try to graph this number 8? Let's try to graph this number 8. Let me see. How do I want to graph this? So z equals to x times e to the -2x squared minus 2y squared. That's what it looks like. Maybe I stop it here and then enlarge that a little bit and then let it run again. Not really visible, huh? Oops, sorry. Yeah, I think this is a better view, but the other way around. Sorry, this is not nice. Yeah, I think this is a better view then. Let's screenshot this one and put it back to our node, and let's put it here. So our 1/2 comma 0 is where you get the maximum, and -1/2 comma 0 is where you get the minimum. Okay, so do we have another way to graph that? Let me see. I'm trying. Let's see. Let's take a look on this graphing calculator. This is actually online. 3D calculator, and c equals to x times e to the -2x squared minus 2y squared. Yeah, that's what it looks like, but I don't like the color. Maybe we enlarge a little bit. I think it's better view, huh? Because it gives us the grids, right? Can you see that? Yeah, maybe this is a better screenshot. Let's screenshot here. And then put it in our notes. Notice I don't use the graph first and then analyze that. No, that's actually the wrong direction. If you, I use the graph only to confirm what I get. Okay, so you see that it reached the maximum. It reached the maximum here. This is the local maximum and this is the local minimum. Okay, this coordinate here is 1/2, comma 0, comma negative, comma 1/2 e to the negative 1/2, while this local minimum here is negative 1/2, comma 0, comma a negative 1/2 e to the negative 1/2. Okay, that's the coordinate. Okay, now that's for number 8. Let's go on with number 12. Now, notice that in number 12, we happen to have a symmetry with respect to xy plane, right? Because if you go note that f(y)(x), if we swap the position of x and y, you still get the same thing, x or yx plus 1 over y plus 1 over x, which is equals to fxy, right? So we have symmetry with respect to y equals to x plane. Now that tells us later on our critical points, if any. Some of them may be the same value a comma a. Okay, but let's take a look. Okay, so the first one, we do the critical points. F sub, you know what, let me rewrite it this way first. This is xy plus x to the negative 1 plus y to the negative 1. So f sub x of xy will be y minus x to the negative 2, which is y minus 1 over x squared. F sub y of xy equals to x minus y to the negative 2. That's x minus 1 over y squared. Okay. Now notice that the domain of this function is all real numbers except the x and the y-axis. The domain of this fxy is all real numbers. I should say all xy where x cannot be 0 and y cannot be 0. Is it right? Now then, if I set this equal to 0, I get y equals to 1 over x squared, which implies x squared y equals to 1. Now likewise, I get x equals to 1 over y squared, so xy squared equals to 1. Now because x and y are both not equals to 0, I can actually divide this, right? Okay, equation 1 divided by equation 2, then I get x over y equals to 1, which basically means x equals to y, as we expected earlier. Okay, now having that fact, then I can substitute into either one of the equation. Let's say I substitute into equation 1. Then I get x equals to 1 over x squared. It implies x equals to 1, therefore y equals to 1. So the critical points is 1, 1. Only one critical point. Step 2, we do second derivative test. So f sub xx of xy will be 2x to the negative 3. Is it right? And f sub yy of xy that will be 2y to the negative 3, while f sub xy of xy will be just 1. So the Hessian will be 2 over x cubed times 2 over y cubed minus 1 squared. When I plug in 1, 1, I get 2 times 2 minus 1, that's 3, that's positive, while f sub xx at 1, 1 is positive, which means that's a local maximum. Local maximum at 1, 1. Okay, that's local maximum at 1, 1. And the value will be, we just plug it in, right? You will see that f11 equals to 1 times 1 plus 1 over 1 plus 1 over 1, that's 3. So that's the local, actually no, not local maximum, huh? F double derivative is positive, so it's supposed to be local minimum, my bad. Local minimum. That's local minimum. Okay, that's for number 12. Number 16, we have that fxy equals to e to the y times y squared minus x squared. Now, this is not symmetry. We don't have the symmetry. So to find the critical points, f sub x of xy will be e to the y times negative 2x. F sub y of xy will be e to the y times y squared minus x squared, plus, I do product rule, e to the y times 2y, which is basically e to the y times y squared plus 2y minus x squared. Now, if I set this equal to 0, notice that e to the y can never be 0. It implies x has to be 0, right? Okay, now if x equals to 0, for x equals to 0, then we will have e to the y squared plus 2y equals to 0. But e to the y cannot be 0. The only way is this guy always positive, right? So the only way is y squared plus 2y equals to 0. You will see either y equals to 0 or y equals to negative 2. So the critical points are 0, 0, 0, 2. Second derivative test. F sub xx of xy will be negative 2e to the y. F sub yy of xy will be ugly. So there will be e to the y times y squared plus 2y minus x squared plus e to the y times 2y plus 2. So that is e to the y squared plus 4y plus 2 minus x squared, while f sub xy will be negative 2x e to the y. Now what happened to the Hessian then? dxy will be negative 2e to the y, that's for f sub xx, times e to the y squared plus 4y plus 2 minus x squared minus negative 2x e to the y squared. Okay, so when I plug in 0, 0, that's negative 2 for f sub xx, and then times 2 for f sub yy minus 0 square. That's negative 4, huh? So that's saddle point at 0, 0. Now, how about at 0, 2? At 0, 2, negative 2e to the y, that's negative 2e squared, which is negative, times e squared to 4 plus 8 plus 2 minus 0 minus 0 squared. But this is negative, this is positive, right? So when you compute, you get negative. This is negative. The saddle point again. Okay, so saddle point at 0, 2. Okay, I will not graph this anymore. Should I? Let's see then. Let's see if I graph that. So what's the function again? E to the y. I have e to the y. Oops, I'm looking at the wrong one. My bad. This one here. I have e to the y times y squared minus x squared. Yeah, we have a lot of saddle point. Huh? At 0, 0 and 0, 2. Maybe enlarge a little bit. See, you see at 0, 0 it's a saddle, right? Okay, how about at 0, 2? Oh, not a nice view. Let's see another way. Let's see GeoGebra. So C equals to e to the y times y squared minus x squared. Ah, not that nice. Yeah, we don't really see the 2, huh? The 2 is around here. At 0 it's clear, it's the saddle, right? But at 0, 2, the 0, 2, I wonder if you can see, it's up there. It's up there. There's 2 here. It's still not visible. Yeah, it's not really clear. Where is that? Yeah, so 0, 2 is the one that we have hard time to see. 0, 2 is the one we have hard time to see. This is 1, this is 2, it's up here. Unless I make miscomputation, let's take a look again. Ah, I write it wrong. 0, -2, not 0, 2. Duh, good thing. Okay, correction. This is -2. Should be -2. So this should be -2 here. So this is negative. This is negative. This is -8. I'm sorry. Good thing I checked. So it should be -8 here. Okay, so no, it's not at 0, 2. It's not at 0, 2. It's at 0, -2. So this is still negative here. This is negative here. And this is also negative, huh? So it becomes positive. So sorry, this is positive. Okay, so no, it's not saddle point. My bad. This is not saddle point. That's actually local max. Local max at 0, -2. Okay, let's see the picture again. 0, -2. It's 0, -2 instead. 0, -2 is this one. It's this one here. I wonder if you can see my my pointer is here. There's local maximum there. Okay, I think this happens to be a nice picture. Let's grab it. Yeah, that happens to be a nice point of view. So we have a saddle at 0, 0, a saddle at 0, 0. No, not the nice one. A saddle at 0, 0, and local maximum at 0, 2, 0, -2. Yeah, this is the positive x, the positive y-axis here. This is the positive x-axis. Okay, so this is the local max. At 0, -2. Yeah, I got it right here. Y equals to -2, but then I plug in wrong one. So it should be the critical point 0, -2. It should be 0, -2. I missed this negative sign here. Okay, at least I corrected. Good thing I checked with the graph, huh? Otherwise, I feel like something not right. Okay, my bad. Let's go on. Number 30 and 32. Find the absolute maximum minimum values of the function on, well, we can find the absolute maximum minimum if we have the restricted domain. That's a closed and bounded domain. For number 30, we have fxy equals to x plus y minus xy. Notice that it is symmetric with respect to y equals to x, right? So we may need that advantage later on. Let's see first. The first step is to find the critical points in the interior. In the interior of D. D is a triangular region with vertices 0, 0, 0, 2, 4, 0. Okay. Now we are interested to find the critical points in the D, inside this triangle. Inside this triangle here. Maybe it's too thick. Give me a second. Let's do it. So we do the f sub x of xy equals to 1 minus y. F sub y of xy, that's 1 minus x, set them equals to 0. So we get the critical points is 1, 1, right? Now let's compute the value right away. What is f11? f11 equals to 1 plus 1 minus 1 times 1, that's equals to 1. So at 1, 1, at 1, 1, the value is 1. Now next, I use wrong notation. It's in the interior. It's in the interior of D. And now then we will talk about the boundary, critical points on the boundary of D. I need to break this boundary into 4 parts. Let's say this is the first path, gamma 1. Let's say this is gamma 2, and this is gamma 3. Gamma 1, or the first, you can also use P1 for the first path. That's when the y equals to 0, the x is between 0 to 4. What happened to the function then? That's fx0 equals to just x, right? That's linear. So no critical points in between. We only have endpoints at 0, 0 and 4, 0, right? The value at 0, 0 is clearly 0. The value at 4 is 4. So actually at this point we have new local max and absolute mean. If I draw it larger so that we have a better view, this is the domain, this is 0, 0, this is 4, 0, this is 0, 2. The value at 0, 0 is 0. The value at 4, 0 is 4. The value at 1, 1 is 1. Okay, now let's see the second path. That's when x equals to 0 and the y between 0 to 2. So f0y, that will be just y. Same thing, we don't have critical points in between, but we have endpoint 0, 0 and 0, 2. Okay, f00 we already know the value is 0. f02, the value will be 2. So at this point we know that the absolute maximum is 4, the absolute minimum is 0 so far. Okay, the last part is we need to find the critical points and endpoints along this path here. Okay, the gamma 3. Let me give myself some space. That's when y equals to negative 1/2 x plus 2. Is it right? Let's plug that in. So fxy equals to x plus y and then minus the product. Yeah, minus the product of x and y. And simplify, we get 1/2 x plus 2 plus 1/2 x squared minus 2x. That is 1/2 x squared minus 3/2 x plus 2. Now, because this is a single variable function already, we can do the first derivative respect to function x, the variable x. Okay, that is equals to x minus 3/2. Set it equals to 0. That gives us the critical point x equals to 3/2. Therefore, the y will be negative 1/2 times 3/2 plus 2. That's negative 3/4 plus 2. Okay, now then we need to find the value. So that's the critical points. So the critical points is, what is the x? 3/2, 5/4, and the endpoints are 0 to 4, 0. Now we already get the value for those endpoints, right? The value at 0, 2 is 2. The value at 4, 0 is 4. But how about the value at 3 halves, 5 fourths? You can plug in x into here if you want, into here, right? Yeah, because the y already a function of x in that case. So this is 1 half, 3 half squared minus 3 half times 3 half plus 2. Okay, that's negative 3/8 plus 2. That's 13/8. So at 3 half, approximately here, 3 half, 5 fourths, the value there is 13/8, which is much less than 4. So the absolute maximum is, so after we compare the value at each corners at critical points in the interior and the boundaries, then we conclude, so absolute maximum is 4 at 4, 0. Absolute minimum is 0 at 0, 0. Okay. Yeah, that's what I think it is. I won't, unless I make any mistakes. I somehow do expect this to be smaller, or maybe negative, but apparently that's not the case. Let me check my computation. X plus 2. Yeah, the slope is negative 1/2, right? Down 2, run 4, next negative 1/2. The y-intercept is 0, 2, that's right. So I plugged it in here, x plus y minus xy. Hold on. See, I make a mistake again. So this is negative. Oh yeah, that's positive 1/2. What am I doing? That's correct. That's correct. 1/2 x squared minus 3 half x plus 2. And the derivative respect to x will be just x minus 3 half. That gives us critical value 3 half. X and the y will be negative 3, 4 plus 8, 4. That's 5 fourths. Yeah. Let's see if I compute it another way, just out of curiosity. So this is x plus y minus x times y. That's 6 plus 5, that's 11/4 minus 15/8. That's 22/8 minus 15/8. Why I get different result? That's 7/8. Plug that in here, that's 1/2 9/4 minus 9/4 plus 2. That's 9/8 minus 18/8 plus 16/8. Oh, that's 7. How do I get that? Should be 9 here. It doesn't change the result though. So it should be 9, this should be 7. Okay, but the local, the absolute max, absolute minimum is still the same. Okay. Number 40. Find the points on the plane that is closest to another point outside of that plane. So let's say we have a plane. This is x minus 2y plus 3z equals to 6. And you have another point 0, 1, 1. Now we want to find the point on this plane that has the closest distance. Okay, I will first do it with the method that we learned in this section. Let's basically pick any point on that plane, call that xyz, and find the distance, call that distance function. In fact, we will do the distance square function. Okay, and then we will minimize that. So x minus 0 squared plus y minus 1 squared plus z minus 1 squared. Okay, now and then let's see, I think I want to solve for x is equal to 6 plus 2y minus 3z. So d squared as a function of yz is equal to x squared, that's 6 plus 2y minus 3z squared plus y minus 1 plus z minus 1 squared. That's the distance squared function. Let's call that our fyz. Now we want to minimize this. We want to minimize this because if the function is being minimized, which means the distance square is minimized, the d will get minimized too, right? Okay, so first we do the critical points. F sub y of yz will be 2 times 6 plus 2y minus 3z times 2 plus 2 times y minus 1. F sub z of yz will be 2 times 6 plus 2y minus 3z times negative 3 plus 2 times z minus 1. Now I need to set these equals to 0. Okay, and then we will, after we solve them, we get the critical points. That should be the point we want at that point, at that time. Let's see. So this will be 4 times 6. That's, so this is, call this equation 1, call this equation 2. Equation 1 will give us 24 plus 8y minus 12c plus 2y minus 2 equals to 0. That's 10y minus 12c equals to negative 22. You know what? Just make it like this. I'm sorry. Just keep it equal to 0. So 10y minus 12c plus 22 equals to 0. Now equation 2, that is negative. That's negative 36 minus 12y plus 18z plus 2z minus 2 equals to 0. Am I right? Okay, so that's negative 12y plus 20z minus 38 equals 0. Let's still call this equation 1 and 2. We now have from equation 1, it's all multiple of 2. Let me divide by 2. 5y minus 6z equals to negative 11. Equation 2, I get, it's all multiple of 2 also, so I get negative 6y plus 10z equals to 19. Dang, I didn't expect it to be this hard. Okay, so multiply this by 6 multiply this by 5. That gives me 30y minus 36z equals to negative 66. Negative 30y plus 50z equals to 95. When I add, I get 14z equals to 29. Is it right? That ugly? I didn't expect that number to be that ugly though. Let me check my computation. What's wrong with me today? I think I did all correct for now. So my z is 29 over 14. How about my x then? As for the x, let me multiply this by, I multiply this by 5 then, and this multiply by 3. So that will give me 25y minus 30z equals to negative 55, and then negative 18y plus 30z equals to 57. So when I add, I get positive 2 on the right hand side, and on the left hand side I have 7y. So y equals to 2 over 7. Using those two, then I plug that into the plane to get the x. So x is equal to 6 plus 2y minus 3c plus 2y minus 3z. LCD 14, 60 times 24, 84, 84 over 14. Does it give me 6? Plus 8 over 14 minus 81 over 14. That's 11 over 14. So the coordinates that we want is 11 over 14, 2 over 7, 29 over 14. There's only one critical number, right? Yeah, so there should be let's make sure that when we use the second derivative test, this is supposed to be the local minimum. It's supposed to be local minimum. But you tried it. Then. My interest is actually to show you the method that we learned even before this. I want to show you another method to do this problem using the method that we have before. What I do first is I find what is the factor normal to this plane. The factor normal to the plane is given by x minus 2y plus 3z equals to 6. So this plane must be normal to factor 1, negative 2, 3. Right? Okay. Now what I want to do next is to find what is the factor. If I pick a random number, a random coordinate on this plane, what that plane can be, or what that coordinate can be. So this is 0, 1, 1 outside of the plane. Okay, and let's pick a point on that coordinate, on that plane. I think 6, 0, 0 will do, right? Okay, so I can create a factor from that coordinate from 0, 1, 1 to 6, 0, 0. Call this factor v. That factor v will be 6, negative 1, negative 1. right? Okay, now the factor normal to this plane, is called this unit normal, call that normal factor n. The factor normal to that plane is 1, -2, 3. What I will do next is to project phi onto n, to project phi onto n. So projection of factor v onto factor n will be, I wonder if you remember, that's phi dot n over n squared times, oops, times factor n. I wonder if you remember this. Is it okay? Now that projection, let me use the green color, that projection will give us this factor here. Okay, now then we will add to it, to 0, 0, 1, 1, that gives us the factor. Let's try. So phi dot n will be 6 plus 2 minus 3 over n dot n will be 1 plus 4 plus 9. That will be 5 over 14 times factor n, which is 1, -2, 3. That gives us 5 over 14, -10 over 14, 15 over 14. Why I don't get what I want? It's different from these answers here. Do I make it incorrect? Yeah. So the point that we want, call this the point on the plane that we want here. What do you want to call this point? What do you want to call this point? Point C. Okay, so point C that we want, according to this, will be 5 over 14, -10 over 14, 15 over 14, plus that 0, 1, 1. I need to use factor notation, position factor. Now that gives me 5 over 14, 4 over 14, 29 over 14. I have issue with this. Only this part are not the same. Let's see. Did I compute it incorrectly? 14 times 6 is what? 4 to 84. That's correct. Yeah, why I get 5 of 14 instead? Let's see, do I make any miscomputation? 1, -2, 3. 1, -2, 3. So 5, -10, 15. That's right. Yeah, I wonder why these are not the same. The X component are not the same. But my YZ are the same, right? My YZ are the same. Unless I make miscomputation here. I honestly don't see my mistake. But using these two different methods, I basically show you these two different ways to do this, right? Okay. Yeah, I wonder why I get different result there. Maybe I'm too tired. I'm sorry. One way to check is this coordinate supposed to be on the plane, right? So it's supposed to satisfy x minus 2y plus 3z equals to 6. Is it right? Don't tell me it doesn't. So 8 minus 3 is 5. It's 5. Yeah, don't tell me it doesn't. It's supposed to be on that plane. Six, 2, -3. So 5 over 14 minus 2 times y plus 3 times that means like 87. Is it equals to 6? Well, it is. -3 plus 87. That's 84 over 14. So what did I do wrong here? See, this gives me, what am I doing? This gives me 92 minus 81, that's right. That's 11, huh? Why is it like that? No, that's not 11 over 14. I make miscomputation here somewhere earlier. 6 times 14. 4 to 84. So that's 84, 14. Multiplied by 2, that's 8. Multiplied by 2, 81 over 14. I'm sorry. I kind of like wonder what's wrong with me. Now I see my mistake. Duh. This should be 29. Duh. So this is 29, this is 87, this is 87, right? So this becomes 5. Duh. Some algebra mistakes. Now I see my mistake. Sorry. So that's minus 3. That's 5 over 14, 5 over 14. Now it matched, right? See what's happened if I make miscomputation. So my technique is still correct. My technique is still correct. Nothing wrong with my technique. I still get the same answer. It's just I make miscomputation earlier. Wow. Okay, let me going in further. Find the points on the surface that is closest to the origin. Word problems, huh? So let's say we have a surface. Okay, let's say that's a surface S, and you have a coordinate and you have a coordinate x, y, z. Call that coordinate c, x, y, z. Let's find the distance from the origin. So distance squared will be x squared plus y squared plus z squared. We happen to have the y squared. That's y squared is 9 plus xz plus z squared. Right? Now call this distance squared our function of xz. The nice thing about this is we have symmetry between x and z. Okay, so the first critical points, that f sub x will be 2x plus c, we will set that equals to 0. F sub c of xc will be 2z plus x. We also set it equals to 0. So z is equals to negative 2x and x equals to negative 2z. How about substituting then? So when I substitute z equals to negative 2 times negative 2z. So c equals to 4c. But that can only happen when c equals to what? Either, I think c equals to 0, huh? Is it right? That can only happen when c equals to 0. Agree? And therefore, the x has to be 0. And therefore, the y squared has to be 9. Okay, so the coordinate will be 0, plus minus 3, 0. Those are the critical points. Okay, now we don't have any boundary, so we need the closest one. So we need to show that these coordinates here will give us the shortest distance, which means we want that to be local minimum, which means when I do the second derivative test and f sub x is 2, f sub zc is also 2, f sub xc is 1. Notice that the Hessian for any coordinate xc will be 2 times 2 minus 1 squared is always positive, where the f sub xx is positive. So at 0 plus minus 3, 0, that will be local minimum. Okay, that's the closest coordinates. As for number 42, the last one, number 47. Find the volume of the largest rectangular box in the first octant with 3 faces in the coordinate planes and 1 vertex on the plane. So this plane is x over 6 plus y over 3 plus c over 2 equals to 1, means the x, y, c intercepts are 6, 0, 0, 3, 0, 3, 0, and 0, 0, 2. Okay, we want a box that looks like this. Okay, so let the vertex of the box on that plane x plus 2y plus 3c equals to 6 b x y z. Then the volume, if the vertex is there, is basically x y z. Is it right? If we want to rewrite that as a function of yz only, then we replace the x by 6 minus something. Which is 6yz minus 2y squared z minus 3yc squared. You see, I noticed that the volume is actually a function of 3 variables x, y, z, but because the coordinate has to be on the plane, I reduce the function of 3 variables now becomes only function of 2 variables. Okay, now then from there I process, find the critical points. V sub y will be 6c minus 4yc minus 3c squared. V sub c of yz will be 6y minus 2y squared minus 6yz. Now we set both of them equals to 0. Now, how to solve that, that's something I don't know yet, but at least that's the approach, right? Okay, I will solve this. I wonder how to do this though. Oh, you know what? So let's call this the first equation and this second equation so that I don't get confused. The first equation, I can factor the z out. So I get 6 minus 4y minus 3z equals to 0. From equation 2, I can factor the y out. That's 6 minus 2y minus 6. Am I right? Respect to c, respect to c. The 6c equals to 0. But clearly x and y, I mean y and c cannot be 0, because if y and c equals to 0, the volume will be 0, right? X, y, z has to be strictly positive. In other words, this implies we have 4y plus 3z equals to 6, and 2y plus 6c equals to 6. Is it okay? Now I solve this further. I multiply this by 1, multiply this by -2. That way I eliminate the y's later on. So when I subtract, I get -9z equals to -6, z equals to 2/3. Plug that into the first equation. 4y plus 3 times 2/3 equals to 6. 4y plus 2 equals to 6. 4y equals to 4. Y equals to 1. And plugging that into the plane equation. Oh, well, anyway, for the critical points at this point, yz, the critical points will be 1 2/3. Okay, 1 2/3. That will give us the largest, I believe. You can do the second derivative test to see if that gives you the largest, the local maximum. Okay, and therefore the dimension, that's the question, right? Okay, find the volume. So the dimension will be the volume will be, you know what, I need to find the x first. What's the x? X plus 2y plus 3c. 2y plus 3c equals to 6. So x plus 2 plus 2 equals to 6. X equals to 2. Okay, so the coordinates associated to the critical points is this. Therefore, the largest volume is the product of those three is 4/3. Okay. The reason I go over this question because I want to show you a technique not described in our textbook, but described by a professor from MIT. His name is Dr. Strang, Gilbert Strang. And this method is also being explained in one of the calculus textbook that I recommend as a supplement. What's the name again? I forgot who is the author of that book. I need to give credit to that person though. Let me see our syllabus. Give me a second. Oh no, I don't mention it, huh? I totally forgot. I'm sorry. But I need to give credit to that person. Wow. One of them is George Thomas Calculus. And the other one is linear algebra. Somebody who is really good in linear algebra. Let me see. Be patient with me. I really want to give credit to that person. I'm searching for it. Oh, Howard Anton. So Dr. Strang from MIT using this technique, and Dr. Howard Anton, he wrote another calculus textbook, but he himself is actually from linear algebra. His linear algebra textbook is how to say that, it's one of the main textbook being used by a lot of people. Their approach is as following. Imagine this plane instead of this plane already there, imagine this plane at 1, 1, 1. So the equation of that plane, x plus y plus z equals to 1. Okay, now the idea is if we have the box with the maximum value, if we have a box with maximum value in this with vertex on this plane, then the volume must be x y c equals to x y c with the restriction x plus y plus c equals to 1. Now what it is doing is actually using the supersymmetry between x and y and c. In other words, if you swap x and y, you get the same plane and you get the same volume function. If you swap the x and c, you get the same thing. If you swap y and c, you get the same thing. In fact, if you permute, x becomes y, y becomes c, and c becomes x, you get the same thing. Okay, With that argument, then with that supersymmetry, then we get x should equals to y should equals to c for that coordinate on the vertex of the box. The coordinate, the vertex of the box on that plane must have x equals to y equals to c. But because they are on the plane, then x plus y plus c equals to 1. Each of them equal to each other. So 3x equals to 1, x equals to 1/3, y equals to 1/3, z equals to 1/3. Okay, so on the plane where x plus y plus c equals to 1, the coordinate on that plane that gives you the largest volume is 1/3, 1/3, 1/3. Now we go back to the original question. X plus 2y plus 3z equals to 6 is actually a plane that you convert from x plus y plus z equals to 1, but you stretch in x direction by 6, in the y direction by 3, and the c direction by 2. Think about that. Think about this. Originally it's 1, 1, 1, right? You stretch that to be 6, 3, 2. Now what happened with this coordinate then? If you stretch in the x direction by 6, you get 2. In the y direction by 3, you get 1. In the c direction by 2, you get 2/3. That's the same answer. Okay, and notice the way they did the work. They don't use any calculus. No, they actually try to benefit from the supersymmetry. I call it supersymmetry, but supersymmetry means something totally different in physics, actually. Okay, I'm just trying to say that now you have a symmetry between x and y, x and z, y and z, right? Okay, if you have those kind of symmetry, then x must equals to y must equals to z. Using the equation of the plane, you get the coordinates on that plane, x plus y plus z equals to 1. Now you stretch that plane, you get the new coordinate for that vertex. Okay, no calculus at all. No calculus at all. Okay, we basically, instead of dealing with let's say, instead of dealing with an ellipse to find the maximum rectangle, you deal with the circle first. Okay, the maximum value for the maximum area of a square of a box that you can inscribe in a circle, for example, must be a square, right? Because of the symmetry, right? And then from there you stretch that for the ellipse. That's the technique. Okay, now notice that I don't really mention this kind of technique in my lecture videos, and therefore I mention that here. Now here is the discussion from our 14.7. I know it's longer than usual, but because I try to give you an insight on how to do problems, a strange problem like this. Now notice that we cannot do this approach if you don't have the symmetry. Okay, yeah. If you don't have the symmetry, then we cannot do that approach. Okay, that's for today then.